So now to better understand how to design a pre-stressed concrete element in with respect to the service load design, let us try it in a sample problem. Design a simply supported pre-tensioned double T-beam for a parking garage with harp tendon and with a span of 18.3 meters or 60 feet using the NSCPC 101-15 or ACI 318M-14 allowable stresses. The beam has to carry a superimposed sustained service live load of 16.1 kN per meter or 1,100 pounds per linear foot and superimposed dead load of 1.5 kN per meter or 100 pounds per linear foot and has no concrete topping. Assume the beam is made of normal weight concrete with FC prime equals to 34.5 megapascal or 5,000 psi and that the concrete strength FCI prime at transfer is 75% of the cylinder strength. Assume also that the time-dependent losses of the initial pre-stress are 18% of the initial pre-stress and that FPU is equal to 1826 megapascal or 270,000 psi for stress relief tendons. So for the solution, so we first have to look what kind of beam are we designing for this particular question. So you can see here that it was stated that the tendons must be harp. So meaning uh, it is classified as a beam with variable tendon eccentricity since it was stated that the tendon is harp. So I think at this point you already know what does a harp tendon looks like. So you can imagine that a harp tendon has variable tendon eccentricity all throughout the length of the beam itself. Although there are some point there, usually at midspan portion that has constant eccentricity. But overall, you can say that that particular beam, a beam with harp tendon, has a variable tendon eccentricity. So with that, knowing that, we know that the right formula to be used for designing this specific problem that we have here is the formula for the beams with variable tendon eccentricity. So we have to use the formulas that we have derived for beam with variable tendon eccentricity, especially part uh, the part of the minimum required section modulus which have a formula equal to this for the extreme pre-compressed fiber and equal to this for the case of the extreme pre-tension fiber. So you can see here that in order for us to compute this minimum required section modulus that can withstand the given demand or loads and uh, also complying with the allowable stresses specified by the code, either NSCPC 101-15 or ACI 318M-14. So in order for us to compute this, we need to know first the gamma, the MDL, the MSDL, ML, and then FCI, FCS, FTS, and FTI. So the denominators here, the FCI, FCS, FTS, and FTI are actually the allowable stresses specified by the code. That is what we are talking about last time when we derived the formula for variable tendon eccentricity. And the M here are the moments due to the dead load, superimposed dead load, and live loads. And gamma is the residual pre-stress factor. So if we know the values of those terms, therefore we can already solve for the minimum required section modulus for extreme pre-compressed and extreme pre-tension fibers. So just to start the solution, uh, just recall that the force acting at the tendons or pre-stressing reinforcements after jacking is equal to PJ, which is the jacking force, supposedly. But again, as we have discussed before, we know that the magnitude of the force, the actual force that will be transferred to the concrete element at transfer stage, is not actually equal to Pj because it experiences what we call pre-stress losses, usually because of the still relaxation of the pre-stressing reinforcement, or it can be also due to the frictional losses happening between the pre-stressing reinforcement and the surrounding concrete duct, and due to anchorage slippage as well for the case of post-tension members. So we know that the magnitude of jacking force is not actually the force that is being transferred to the concrete element that transferred, but a reduced magnitude of force, which is actually what we call the initial stressing force. And then after that initial pre-stressing force is transferred to the concrete element, it will again experience additional pre-stress losses that will eventually result to what we call the effective pre-stress force. So this term here is actually described on the question itself. So the question said that we have to assume that the time-dependent losses of the initial pre-stress are just 18% of the initial pre-stress itself. So meaning the magnitude of these stresses, or the magnitude of these pre-stress losses that are supposed to be experienced by the pre-stressing reinforcement are just equal, or is just equal to the 18% of the initial pre-stressing force. Or in equation form, it is equal to 0.18 of PI, the initial pre-stressing force. So if we will simplify this equation and then just divide the whole equation by PI, we can have this relationship. And if you can recall from our previous discussions, the ratio of the initial, or the ratio of the effective pre-stress force and the initial pre-stressing force is equal to gamma, which is the residual pre-stress factor. So if you can relate these two terms here, you can say, or you can easily see that gamma is equal to 0.82, meaning the residual pre-stress factor is just equal to 0.82, according to these equations that we have here. So after that, since we already know the gamma, the next thing that we have to find are the allowable stresses specified by the code. So if you can remember, at initial pre-stressing at transfer with self-weight, which is this is the concrete element that we are designing. So again, we know for a fact that the critical section for beams with variable tendon eccentricity is actually the midspan section. That's why we will depend the maximum permissible stresses specified by the code with respect to the midspan section. So we know that at the initial pre-stressing at transfer with self-weight, there is a pre-stressing force acting on the pre-stressing reinforcement with a magnitude equal to P. And that P will tend to bend the beam upward, making it a simply supported beam, resulting to that results for the beam to support its own weight W sub dl. So because of these things being experienced by the concrete element at this stage of pre-stressing, there are stresses that are induced inside the concrete element, specifically at midspan section, which is the section that we are considering for the allowable stresses specified by the code. So if we will just uh, call the extreme pre-compressed fiber stress equal to FCI, and the stress at the extreme pretension fiber equals to FTI. And if we will just recall that according to the code, if you will refer to NSCPC 101-15, section 424.5.3, you can see this table. Although you can also refer to ACI 318M-14, you can also see similar table. So according to the code, a transfer stage, a transfer of pre-stress, the code states that the maximum compressive stress that can be experienced by the concrete immediately after transfer or simply at transfer stage are just equal to these limits specified on the code. So you can see here that according to this table, if the location of the section that we are concerned uh, is located at the end of simply supported members, the maximum compressive stress is equal to zero point 0.7 of the initial compressive strength. Although, since we are not considering the ends of this simply supported beam that we are designing, we are concerned on the second row of this table, which is for all other locations. So according to that, uh, the maximum compressive stress that can be experienced by our concrete at transfer stage is just zero point 0.6 of FCI prime. So you can see here on the stress diagram, the compressive stress part uh, is this, the lower portion of the beam. So this maximum compressive stress here acting at the concrete element at midspan at transfer stage, according to the code, must not exceed 0.6 FCI prime. So if we will just substitute the corresponding values of FCI or FCI prime, which is stated on the problem that uh, that that is just 75% of the compressive strength of the concrete. So we can compute for the magnitude of FCI prime, which is just again equal to 75% of the specified FC prime uh, specified on the problem. So if we will just multiply that to 0.6, we can now find the maximum compressive stress, which is 15.525 megapascal, that is allowed to be experienced by the concrete element at transfer stage according to the code. And then in a similar way, according to the code on NSAPC 101-15 section 424.5.3.2, you can see this table on that particular section. And also you can see similar provision if you will refer to ACI 318M-14 section 24.5.3.2. You can see similar table that states the maximum tensile stress that can be experienced by our concrete element that we are designing at transfer stage. So again, similar to the limitations of the compressive stress, uh, the the maximum tensile stress that can be experienced by the concrete element at transfer according to the code are just equal to these limits that are enumerated here. And again, we are not concerned here on the end supports or end location at this simply supported at this simply supported beam. We are concerned actually on the midspan, which is actually included on the all other locations classification here, which states that the maximum tensile stress that can be experienced by our concrete element at transfer must not exceed 0.25 of square root of FCI prime. So again, just substituting the corresponding values, we already computed the magnitude of FCI prime, which is just 75% of the FC prime specified by the problem. We just have to take its square root and multiply to 0.25 in order for us to find the maximum tensile stress, which is 1.272 megapascal, that is just allowed to be experienced by our concrete element that we are designing at transfer stage according to the code. So these are the limiting stresses that are specified by the code. So if we want our design to be code compliant, therefore we must make sure that the maximum tensile stresses as well as the maximum compressive stress that will be experienced by our concrete element at transfer stage must not exceed these values that you are seeing here. So obviously after that stage of pre-stressing, the service load condition stage will now enter, wherein additional loads will be carried by our concrete element that we are designing, which are coming from the superimposed dead loads and live loads. And because of that, there will be additional bending moments that will be produced on our midspan section, which will eventually produce what we call additional flexural stresses. So if you will try to look what will be the total stress diagram that will be acting at midspan section when this additional loads already acts on the beam, the stress diagram will look something like this. So if we will just call the extreme pre-compressed if we will just call the stress at the extreme pre-compressed fiber equal to FCS, and let us just call the stress at the extreme pre-tension fiber equal to FTS, we will and if we will just recall that again, according to the code, the stresses that you are seeing here must be limited to a certain magnitude of permissible stress, which is again enumerated on the code, which can be found on NSCPZ 101-15 section 424.5.4. You can see that you can see this table on that code, on that particular section of the code, and again you can see similar provisions on ACI 318M-14. Although again you just have to take note of the some of the typographical error on our local code. So you can see here the code states that the maximum compressive stress at service load condition is a function of the FCI prime, which is the initial compressive strength, wherein actually it is a function of the compressive strength itself. So I think that is just a minor typographical error. That's why it's worthy to cross-check the our own. It is worthy to cross-check our own local code to the reference code, reference international code. So again, according to this particular code provision, at service load condition, our concrete must experience a maximum compressive stress that must not exceed the stresses specified here. And again, we have two options here. So the question now will be which category will we fall into? So again, we are not considering total load here. We are just considering service loads, or in other words, the sustained loads. So we will be included on this classification here, the first row. So according to this table, the maximum compressive stress that can be experienced by the concrete element at midspan section at service load condition must not exceed 0.45 of FC prime. So if we will just substitute that on the equation itself, recalling that FC prime is equal to 34.5 megapascal, we can see this maximum allowable compressive stress that can be experienced by our concrete element at service load condition conforming to the code provision, which is this. So again, at service load condition, the stress diagram will look something like this, which will now have compressive stresses acting on the upper portion and tensile stresses acting on the lower portion. So again, this stress at the extreme pre-compressed fiber must not exceed this stress here, the 15.525 megapascal stress that we have computed conforming to the code provision or code limitations. So for the case of the limitations for the tensile stress acting on the extreme pretension fiber, we can refer to 424.5.2 from NSCPC 101-15. Again, you can see this table and similar table from ACI 318M-14 section 24.5.2. So again, since we are on service load condition, we know that the purpose of this checking is to ensure that uh, our precise concrete element that we are designing will not experience cracking. And according to this table, you can say that the concrete already cracked when the stress acting at the uh, tensile. I mean, according to this table, you can say that the concrete is already cracked when the tensile stress acting on it is already greater than this term here, which is the square root of fc prime. So therefore, the maximum stress, the maximum tensile stress that can be experienced by our concrete element at service load condition, in order for us to say that it is still not cracked, is this term here, this stress here, which is the uh, square root of fc prime. So that is the maximum tensile stress that can be allowed to be experienced by our concrete element at service load condition, for us to still say that it is not it is still not cracked. Because according to this table, if the tensile stress is already greater than that term square root of fc prime, therefore we can already say that our concrete already cracked, and we don't want that to happen. That's why we are conducting pre-stressing, and that's why we are conducting service load design. So meaning this tensile stress that you can see here is limited to this magnitude of tensile stress, 5.874 megapascal. So again, Fc prime is just equal to 34.5 megapascal. And if you will just take the square root of that, you can get this value here, 5.874 megapascal. Meaning, the maximum tensile stress that can be allowed to be experienced by our concrete element at service load condition must not exceed this stress that you are seeing here. So those stresses that we have derived from the code are actually the stresses that we can use for finding the minimum section modulus required to resist the given demand or loads. So in addition to those terms that we already derived, the last things that we need to compute in order for us to derive the or compute the magnitude of the minimum required section modulus that can resist those given demands or loads here are just the moment due to dead loads, due to the superimposed dead load, and live load. So those are the remaining terms that we have to compute in order for us to compute for the minimum required section modulus. So for the case of the moment due to the superimposed dead load and live load, we can easily compute them because the magnitude of the service live load and the superimposed dead load are already given, and we know that the maximum moment that will be induced in a simply supported beam will act at midspan with a magnitude equal to WL squared over 8. So we can just substitute this W specified on the problem and the length of the beam, which is the 18.3 meters, and then for us to be able to compute for the MSDL and MLL. But now, the major problem here is how to compute MDL, the moment due to the dead load or the self-weight of the member itself, because we don't have a section to begin with. That's why we are conducting design, right? We we still don't have a section for us to compute the self-weight of that section to be substituted on this formula that we have derived. So that will be a major problem on this computation. Although we have a solution for that. So the solution is we can assume we can assume a certain section, what we call the initial section. We can assume an initial section just for the for the sake of for us to be able to compute a moment due to the dead load or self weight. So in this case, on this particular problem, I just arbitrarily chosen the uh, I just arbitrarily I just arbitrarily chosen the 12DT34 double T section. So you can refer to the PCI design handbook for you to be able to see the properties of this particular section that I have chosen. So if you will refer on PCI design handbook, actually I refer on PCI 2010. So the properties that I will use here are all came from, uh, the properties that I have used on this particular problem just came from PCI 2010. So if you will refer to PCI 2010, you can see the self-weight of 12DT 34 double T section. Although, if you will refer on PCI 2010, you can see there that the given properties are all in terms of US customary units. So you just have to convert them into their corresponding SI units. So if you will convert the weight specified on PCI 2010, if you will convert it to SI unit, you can have this magnitude of self-weight of 12DT 34 section. So again, take note, this is just an assumption, meaning uh, you can have your own different assumed section here because we just have chosen this section arbitrarily. Did I pronounce it correctly? Arbitrarily. Okay. Although again, just like what I've said, you can choose any other section. Actually, you can choose the largest section available on PCI 2010, which has a self-weight equal to 18.02 kilonewton per meter. So actually, you can use that if you prefer to use that. But for me, I just arbitrarily chosen the section 12DT 34 for my initial section. Actually, if you can remember from our introduction to this flexural design of precast concrete elements, we have said that the design requires what we call preliminary section or preliminary design or preliminary section in uh, specifically in particular. So we cannot commence the design process itself if we don't have uh, an initial section. So the importance of the initial section is actually due to the consideration to the soft weight, because we cannot commence the design if we don't have magnitude of self weight to begin with. So again, if in order for us to have at least uh, an initial self-weight to be used on this formula, we can just assume a specific section specified on the PCI 2010 Design Handbook. So again, as I've mentioned a while ago, for a simply supported beam, the maximum moment occurs at midspan with a magnitude of WL squared over 8. So we can just use that formula for us to be able to compute the corresponding MDL, MSDL, and MLL. So for the MDL, moment due to the dead load, we just have to use the weight of the dead load that we have assumed, which is 14.88, and this is the corresponding moment due to that load. So for the moment due to the superimposed dead load and live load, we can just substitute WL squared over 8 for MSDL and add it to WL squared over 8 for MLL, or we can just combine the two so that the resulting expression will be equal to this. So again, this expression is just equal to this. We just combine the L squared over 8. I mean, we just combined we just factored out the WL squared over 8 actually. We just factor out the I mean, we just factored out the L squared over 8 on the supposedly expression that we will have here. We just factored out L squared over 8. So the resulting expression will now be equal to this. And if you will compute that, the result will be equal to this. So this is the sum of the moments due to superimposed dead loads and live loads. So with that, we already computed all of the terms that we have to substitute here on these formulas for us to be able to compute the minimum required section modulus that can withstand the given demand or load conditions. So substituting all of those on the corresponding formula, taking in consideration the consistency of units. Just for consistency of units, since we have used megapascal or Newton per mm squared for the stresses, we can might as well just express the moments in terms of Newton mm. So we just have to multiply them by 10 to the 6 because we need to convert kilonewton to Newton and meter to mm. So in order for us to compute, in order for us to convert kilonewton to newton, we have to multiply it by 1,000, as well as meter to mm. We also need to multiply meter to 1,000 to convert it to mm. So the product will be a total of 1,000 squared, or 10 to the 6. So again, just a note again, you have to include the corresponding signs of the stresses, because we are talking about stresses here. And we know that stresses have magnitudes and directions. So you have to specify the corresponding directions of the stresses that you will substitute here. So again, if you can remember, FCI is actually a tensile stress. So we just have to put a positive sign there. But FCS, the extreme pre-compressed fiber stress acting at service load condition, is actually a compressive stress. That's why we have to include the negative sign here to indicate that it is actually a compressive stress. So computing that equation, we will have this minimum required section modulus with respect to the extreme pre-compressed fiber. So this means that the minimum required section modulus that must be present to the section that we are designing in order for it to withstand the given loads here, must be, or must have, a minimum value of 51,235,939.80 mm cube. So again, the resulting units or unit from this expression will be mm cube, because we already had, or we already have a consistent system of units. And then substituting to the other formula, we will find this minimum section modulus with respect to the extreme pretension fiber. So again, these are the minimum section these are the minimum section modulus that is required to be uh, to be present on our section that we are designing in order for it to resist the given demands here on the questions or question, as well as in order for it to be in conformance to the maximum permissible stresses specified by the code. So if you will choose the sections specified on PCI 2010, specifically the pre-top double T load tables that can be found on section 3.5, you can see there a series of different sections with different sizes, with different properties, specifically the section modulus. And if you will try to look at them, uh, all you need to do is uh, find a section there that has at least a section modulus with respect to the extreme pre-compressed fiber, which is the top fiber, which is equal to this magnitude, as well as for the section modulus with respect to the bottom fiber. You just have to find a section there on PCI 2010 that has a minimum section modulus with respect to the bottom fiber equal to this magnitude that you are seeing here. So if you will refer on PCI 2010, you can see there that this particular section, and this particular section, and this another section. So again, these sections are again chosen arbitrarily by me. So these are my candidates for our design. These are my candidates that I feel that can be that can withstand the given demand on the problem itself. And these are the specific sections that has, or that have actually the minimum section modulus specified or computed here. So if you will take a look on this particular section, the 10DT26 double T beam, if you will look on the uh, section modulus. Again, if you can notice, all of the properties given on PCI 2010 are all in US customary units. So it is actually a requirement to convert this value that we have computed to its corresponding US customary units. So we just have to divide this actually by 25.4 mm cube. So we have to raise it to the power of 3 because the unit is in power of 3. So again, that is just a simple conversion. I hope at this stage, at this level that you are into, I hope you already know how to convert units. So if you will convert this to its corresponding US customary units, it will have a value equal to this. You will compute this values that you are seeing here in terms of US customary units. So with that, with this given minimum required section modulus, just have to find a particular section here that has a section modulus greater than or equal to this section modulus that we have computed here. So if we will take a look first on the section 10DT26, specifically on these properties, you can see here that the section modulus with respect to the top fiber is equal to 5379 inches cube, which is obviously more than the minimum required that we have computed. So in terms of that section modulus, this section is okay. But if you will take a look on the section modulus with respect to the bottom fiber of this particular section, obviously it has a less magnitude of section modulus with respect to the bottom fiber compared to the required that we have computed. So therefore, this section cannot be an option actually for the design of this particular section that is specified here. So we have to search for another section that can satisfy this minimum section modulus requirements. So if we will take a look again on other sections, specifically 10DT34, and look on its section modulus properties, you can see that its section modulus with respect to the top fiber is equal to 9046, which is obviously greater than the minimum required. So it's okay. It's okay with respect to the section modulus with respect to the top fiber, and as well as with respect to the bottom fiber. So this section here has a section modulus with respect to the bottom fiber equal to 3222, which is obviously greater than the minimum required. So therefore, this section can be an option to this design that we are doing. But if you will take a look again on other section to find other candidates, uh, say for example this 12DT34 section, if you will refer to the section modulus of this particular section, you can see also that the section modulus with respect to the top fiber and bottom fiber also satisfies the minimum requirement because obviously they have a larger, or I mean obviously it has a larger section modulus with respect to the top and bottom fiber compared to the minimum required here. Therefore, 12DT34 can also be a candidate for the design of this particular double T that we are designing. So now the question now will be, since we have two candidates here, the question now will be, which of them will be the governing design? So that will be the very big question that we have to address here. Which of these uh, two sections will we use as the design section for this particular problem? So take note if you can remember the initial section that we have assumed is 12DT34. So Does that mean that uh, we we will prefer it to be used for this particular problem, just because it is the initial section that we have assumed initially a while ago? So will it be the governing section that we will use on this particular section? So actually, uh, you can use any section actually, as long as the minimum required section modulus uh, 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 is satisfied by that particular section. So since both of them satisfy the minimum section modulus, therefore both of them can be used depending on the designer himself or herself. But but take note, since we are civil engineers here, we are economical designers. We often design economically, meaning our design must always be, or our design must always incur minimum cost. And if you will compare these two sections that we have found out here, if you will compare their total weight, you can see here that the weight of 10DT34 is just 891 pounds per linear foot, while the 12DT34 has a somehow uh, uh, heavier, or somewhat heavier weight compared to this 10DT34. So given that information, given that this section is heavier than this section, given that information, which of them do you think will will produce an economical design? So obviously, if the weight is less, we can expect that the materials needed to produce that particular section will have a lesser cost compared to a similar material or similar section that has a larger weight. So larger weight means larger uh, larger requirement with respect to the materials needed. For example, for the volume of the concrete that is needed to be poured for this particular section. And since we have a larger volume of concrete, say for example, that is needed to produce this particular section, therefore there will be more costs that it there will be more costs that this section will incur. So given that limitations, therefore we can easily say that between these two, between 10DT34 and 12DT34, we will prefer to use 10DT34 since it has a lighter weight. Therefore, it will incur lesser costs in terms of production. So therefore, let us just use the non-top normal weight concrete 10DT34. So we will prefer to use this section over this section. But then again, may I just clarify, you can use this section. There is no one that prevents you from using this. Especially you are the designer of this particular structure or member that we are designing here. So again, it is the responsibility and of the designer. I mean, it is the right of the designer to choose whichever section he or she will want to use for his or her design. So you have all the authority to do that. If you are the designer, you just have to take note that you also have the responsibility to produce an economical section. So again, given that responsibility, we will just prefer to use this lighter section, which is the 10DT34. So again, that 10DT34 uh, satisfies, obviously, this 10DT34 will still satisfy the minimum section modulus that we have computed here. So you can just substitute the uh, actual moment due to this self-weight of this particular section in place of this assumed moment due to dead load. So again, take note, this term here is just assumed. If you can remember, we just assume an initial section, which is this, which will produce a moment which will be equal to this. But since we preferred to use this section, you can check you can check its adequacy with respect to the required minimum section modulus if you will compute for the moment due to the self weight, which is this. So if you will compute that moment due to this self weight specified here and substitute it here on this formula that we have here, obviously you can compute for a lesser magnitude of section modulus, meaning uh, the required the resulting required minimum section modulus will be uh, much less than the required section modulus that we have computed a while ago using the assumed section. So meaning it will be more satisfying. That's what I'm pointing out.